Here's the scenario. I want to talk about D-types and problems related to D-types that you can run into implicit conversions, or the case of things where maybe you lose some data, maybe there's a correctness issue. And so the setup is as follows. I have a data frame, and that data frame is maybe collecting some information that I have drawn from a data center. Maybe I'm doing some analysis of devices in the data center, and maybe I have some relationship between faults on those devices, warning messages that are emitted, and information about either the power usage or, in this particular case, say the temperature usage. And so I have, as part of my theory, maybe, for example, an idea that maybe my GPU has some faults and that's causing a power spike and that's causing a temperature thing, or maybe it's the other way around. Maybe the temperatures are predicting the faults. Maybe whenever I see the temperature rise to a certain point, I see a fault in the GPU that maybe cancels my machine learning job. Whatever the case may be, I'll start with a fairly straightforward data frame. And the data frame is going to look like this. It's going to be looking at one device, and it'll have a column that measures the faults that I see and a column that measures the temperature that I saw around the same time. Now note that this is per day, so maybe these are averaged, or maybe this is something that we could look at higher fidelity, whatever the case may be. When I look at this data, I might be interested to kind of get a sense for what the distribution of the faults are. And so you can see that this data is mostly randomly generated data. We shouldn't worry too much about the dummy data that we're looking at for each of these examples. But here you can see the faults are just some skewed normal distribution. And so the distribution of those, you should mostly see 0 faults. And you'll see a couple of faults of 1 and a couple of faults of 2 with a little bit of extra work just to make sure we don't get a negative value. And we always get an integer value here. The temperatures are, of course, centered around 70 degrees Fahrenheit, and so our data is fairly straightforward. Except, I might be looking at not such a small amount of data, here about 90 rows, but I might be looking at thousands upon thousands of rows of data, and I might even be doing some sort of analysis that requires sending this data off to a model, maybe a model running on my GPU. And as a consequence, I might be very sensitive to the amount of memory that I'm using. And so one thing that I might do is I might be very careful to make sure that the data that I'm looking at is stored in the smallest possible type. For example, the faults are either 0, a 1, or a 2, so I don't think I need more than an int with 8 bits in order to store that. I probably will never see 255 faults on one single day on one single device. And the temperature, well, the temperature maybe if, for example, I'm predicting this thing, we know that especially for these extremely large models, we can get significant speed ups or significant capabilities we simply don't have in the ability to run one of these things. If, for example, we take our float 64s and we downcast them to float 32s or float 8s, we can oftentimes double or even quadruple the amount of work that we can do on a given GPU, and consequently double or quadruple our cost savings by downcasting these floats. So we'll make these float 32s. So if we take a look at this data frame, we'll see, we have some, let's take a look at our info, and you can see we have 90 in 8s and 90 float 32s. And there's going to be some information loss here, especially with the float 32, but we can actually put a bound around that. So we could look at the original temperature. We could subtract what happens when we downcast that to float 32. We could take that result and bin it and find 5 bins and then see how the data fits in those bins. And what we'll see is, for the most part, our error is quite constrained. For the most part, all of our error fits into this bin right here, less than 0.00002. So, we may not worry that much about that because our actual measurement mechanism may really only have 2 digits of significant failures anyway. And so, that kind of error we can deal with. Well, taking that general idea of using the smallest possible type, we might find that when we are looking at not just one device, but multiple devices, and we're going out to every one of these devices and collecting this information from them, well, we may discover that we want to always find a way to make use of the smallest possible data type, the smallest possible t-type. So we'll always do these as-type conversions. And so here in this example, we have a bunch of different devices. We've gone out to those devices and we've collected we've collected individual series of measurements from them, and we're going to downcast each individual series to int32. So if we take a look at the devices that we have, we can see our keys here are each of the individual devices. These are kind of host names. And if we look at one of these devices, you can see we have these int32 of this counter measurement that we have. Now, with that data, we may want to answer questions. And of course, we'll have to concatenate this data up in order to turn it into one data frame that we can operate on. So we'll concatenate this data up, and then we might answer questions like, what were the total number of faults that we had in a given time period? So we might do a group by on the month in order to see, these are the number of faults that we had per month. That's a lot. I guess this must be a very incremental counter. Maybe a packet drop is what the fault is. That would kind of make sense why this counter value would be so large. And we might choose not to use pandas.grouper, because one unfortunate thing about the pandas.grouper is that the index that it gives us here doesn't really reflect the periodicity of the grouping that we have. It's just the end date of that period, the 29th of February in the case of this leap year, versus the 28th of February if this weren't a leap year. It's just the last day in that month. And so that's kind of messy. So we might end up having to do something a little bit more complicated. We'll do a group by with an index transformation. We'll take that index, we'll transform it to a monthly period, and then we'll do the group by and the sum together. And so we get something that's a little bit nicer here. Now, obviously, we're going to want to do something with this data. We're going to maybe want to unstack it into each individual device and then plot it, perhaps even do an aggregation to try and get a sense across these rows. What's the minimum number of faults and what's the maximum number of faults? But before I reveal the final block of code here, I have a question for you. Can you spot where this code might kind of suck? And I'll bracket your search by a couple of notes. One, don't worry about places where pandas might not quite have an API that's consistent enough or complete enough to solve these problems easily. There's always just a little bit of clumsiness whenever you're using pandas as a consequence of the API still being under active development and often having places where you can do something in this particular method, but you don't have the exact same keyword arguments in that method. So don't worry about that. And don't worry about the case where, for example, you can say this is kind of complicated. Maybe we could break it down into individual steps and we could have each line. Don't worry about formatting. Don't worry about chaining. I always find the most inane thing anybody can talk about when it comes to pandas is the difference between multi-line and chaining. There's actually something here that is a correctness issue or a potential correctness issue. And given all of those hints, can you spot what might kind of suck about this code? If you said that the key to understanding how to avoid a certain class of correctness issues in pandas is understanding places where pandas likes to implicitly upcast your data, even if you've downcasted it, and if you said this is tied to the introduction of additional new D types that we have available, extended D types that we have available, if you said that this code kind of sucks because it's not really making use of features that we have in pandas, in other words, that this code doesn't use a capital I in 32 instead of an in 32 with a lowercase I, well, you're absolutely correct. Because obviously when we do some analysis with this code and we aggregate it to get the result, you'll see that the min and the max, which should reflect the counts, the values that we have, well, it's reporting this as floating point data. And you can see the reason that's reporting this as floating point data is when we did that unstack operation, missing information that needed to be represented on this last row here, because not all of the data spread all the way into April of this year, turned into nans, and Pandas said the only way for me to represent nans alongside numeric data is if I use an in-band encoding, is if I use a floating point type. So I'll throw away the int32 encoding and I'll upcast everything to float64. Well, this kind of sucks. And we do have some opportunities to improve this code. Obviously, the easy answer might be, instead of using the lowercase I int32, we could use the capital I int32. And when we do that, we might see that the result here of this aggregation keeps the data as int32, that when we perform just the unstack alone, we get this angle bracket NA. And you might not be aware, but this may actually have as a consequence direct correctness issues. As is always the case, this one narrow example and this one narrow piece of code is never as interesting as the broader idea and the broader problem. So let's talk a little bit about what's really going wrong here. What we know is that in pandas, we have different ways to represent the D type, the data type of some data that we have. And this D type phraseology is something that we borrow from NumPy. If we have a NumPy and D array, we can create a NumPy and D array by passing it raw Python data. But a NumPy and D array represents an interpreted view of raw memory, and so it has some typing information, how that underlying raw memory should be interpreted. And we have options. We can pass these as strings, or we can actually import these things if we want. We can say, you know what, interpret this, take this Python data, convert it to machine int32s, and put it into a raw block of memory, and then the interpretive layer will say, well, that raw block of memory is now interpreted to be int32s. We can play all sorts of tricks with this. Like we can say, you know, even though the data was originally converted to int32s, we can say now reinterpret this as effectively a free operation as int16s. And so now we see instead of 3 values, we see double the number of values because each one of those int32s is now being viewed as 2 int16s. So we can play some tricks there. Well, pandas as an intermediate layer sitting between your pure Python code and your NumPy code as a layer that adds one more set of abstractions on top of NumPy, introduces additional D types beyond those that are available in NumPy. And so if we take a look, not a NumPy and D array, but a pandas array, and here I'll change the name of this just so that it's very clear, we can actually tell the pandas array, okay, create a pandas array with a D type. And now this intermediary level allows us to do a lot of neat things. It allows us to, for example, represent categorical values as a mapping separated from the original raw data. But in the case of this D type mapping, well, one of the things that we can do is instead of making this a lowercase int32, we can make it a capital I int32. And that seems like the most trivial change. It seems like that really shouldn't make a difference in our lives, but it ends up making a huge difference. Note that by using that capital I int32, what pandas has done is instead of storing this as this NumPy and D array with just this very thin wrapper on top of it, it's now actually storing this as something equivalent to a NumPy masked array. It's actually storing 2 pieces of data. It's storing the raw data, the 1, 2, 3 values, as int32 values, and it's storing a mask. And this mask, this out-of-band encoding, allows this structure to now represent missing values without upcasting the data. Whenever we talk about in-band versus out-of-band encodings, and we've talked about this before in many other contexts, what we're really talking about is, do we use the same channel to represent data and metadata? And when we talk about out-of-band, we're talking about, do we use distinct channels to represent data and metadata? Well, if you think about it, the float IEEE 754 double precision floating point standard, so IEEE 754 float, is basically an in-band encoding of either some data, some numeric value, or some metadata, some erroneous case, like a float nan. And if you think about the bit patterns here, I don't know that I can give you the bit pattern for 1.23 off the top of my head, but you can imagine there's some bit pattern. I'll just put something here just off the top of my head. And then there's some bit patterns that are carved out of this for, and imagine this continues on for 64 bits. I'll put a ... just to make it, just to cover myself there. Well, you can imagine there's certain bit patterns that are partitioned out of the space of all the possible bit patterns for representing a 64-bit float to represent things like nans, negative infinities. In fact, in IEEE 754, there is not one nan, but there's actually an entire set of payload nans. You can actually have a nan with some additional information associated with it. So you can represent some very rich metadata. Unfortunately, most of the tools that we use, NumPy and pandas, don't really do much with payload nans, but it is available to you from the underlying formulation. What you can think is when you look at something like an int32, a machine representation of a 2's complement signed integer, every bit pattern is already taken by a value. So any arbitrary bit pattern we can come up with, well, there's a corresponding value associated with that. And unless we can do some additional partitioning of our data, that is to say, unless we can say, well, these are counts. So a negative value means not available or missing, because you can't have a negative count. It's nonsensical. Well, in the absence of being able to do that, we really can't represent missing information. We can't represent metadata. We can't represent anything that's not of value in this int32. As a consequence of pandas being this generalized tool, pandas can't say, well, I'm guessing you're using a count here, so I'll just have a -1 representing a missing data. That's too specific to one person's use case. Pandas has no choice but to upcast from whatever your integer type is to some floating point type if it ever needs to represent missing information. And many common operations that you'll perform in pandas will require that you represent missing information. Because if you think about it, when you have some data frame, and that data frame has some index level, let's give this 2 levels on its index. There's XA, XB, and YA. And we do a shape transformation on this. We do an unstacking operation. Well, what we're going to end up with is we're going to end up pulling one of these levels up into the columns. So if we were to unstack that X and Y level, we'd have X and Y here, and we'd have these 2 layers remaining. Well, there was no entry for Y and B. So what is pandas going to put here? It has to put something representing that the data is missing. If that data was originally in 32 data or even in 64 data, pandas really doesn't have a choice then to represent this as a floating point piece of information, as a floating point nan, forcing all of these other values to be converted to floating point. Well, this starts to get very problematic, especially if we have really large values. Because remember, IEEE 754 has some aspects of it that make it significantly harder to work with than just regular old integer values and integer mathematics that we're used to. IEEE 754 cannot be compared directly for equality because IEEE 754 is not associative, it's not commutative, and it has problems with exactness, and it has problems with precision. Or I shouldn't say problems. Of course, this is a very careful design in order to satisfy the needs of a very disparate set of users. But as a consequence, a lot of things that are just easy to do in integer math, in integer computations, become much harder in IEEE 754 floating point operations. For example, we can no longer directly compare for equality. Some integer operation is directly equivalent to another integer operation irrespective of whether we change the order of the terms or we change the grouping of the terms. But that is not the case in IEEE 754. In other words, if we have some specially picked values, and I'm going to pick these values very specially. So we'll choose 2 to the 53rd plus 1. We'll choose negative 2 to the 53rd plus 1, or minus 1. Here we'll make it like that, or actually I'll negate it on the outside. It makes my life a little bit easier. And we'll choose the value, I don't know, of 1. It's no longer the case that adding these together with a particular parenthesis or order of parentheses with a particular grouping will result in the same end answer. In other words, if we group X and Y together and we add them first versus if we group Y and Z together and we add them later, actually let's do X like that and that. We'd actually get different answers. And if we were to then multiply this by something, we could get yet another answer because multiplying times 1 versus multiplying times 0 starts to really compound the differences that we see. IEEE 754 is actually quite sensitive to the order of operations that are picked. And if we were to have original computations that are done with all of the assumptions of integer math, and then suddenly pandas silently upcast this to float 64 math, well, a lot of things that we might just naively anticipate would just work in the rest of our code may no longer just work anymore. Well, this can be problematic. We can even lose data. This value, 2 to the 53rd plus 1, is very specially picked. And the reason that I know to pick this particular value to demonstrate problems that we might have taking naive approaches to mathematics done in floating point is, well, we're talking about 64-bit floating point values. And I don't know exactly how to write out the bit patterns for any given floating point value. That's a little bit beyond me, but I kind of know how this is laid out. I know that of those 64 bits, there's a signed bit. I know there are some fractional bits, and I know there's an exponential bit, and there's a lot of complexity around normalization and whatnot. Well, I kind of know how many fractional bits there are, and I know how many exponent bits there are. I know there are 53 bits for the fractional component, because IEEE 754 is basically you take some fractional component, you raise it to, an exponent. It's kind of like this, but there's actually more than that. You actually do like 1 plus whatever for non-denormalized values. But whatever the case may be, now there's 53 bits here. It turns out that 2 to the 53rd plus 1 in 64-bit float is the first value that cannot be exactly represented. In other words, 2 to the 53rd plus 1 is the first value when, if you add 1 to it, it doesn't change. 2 to the 53rd plus 1 is equal to 2 to the 53rd plus 2, which means not only do some of the naive things that you can just easily do in integer mathematics no longer work, but you could even lose data. If you happen to have integer data that was this large, that were values that are as large as this, and you silently upcasted this to float 64, you would no longer be able to maintain the distinction between these two values. So you'd no longer correctly represent that one of these is 993 and the other one is 994. You can actually lose data as a consequence of this. This is why we want to be very careful whenever we're working with very large values. And of course, thankfully, we have 64-bit machines, and 2 to the 53rd is a very, very large number. So we're not going to run into this problem if we're just counting the pennies in our piggy bank. But it is the case that rather than allow pandas to do this implicit upcasting, we will actually want to be fairly careful about using the extended D types, these capital I in 32 or capital I in 8D types, because as a consequence of giving us this out-of-band encoding, as a consequence of representing this value in this kind of masked integer array approach, the data separated from the mask, we have the ability to represent missing data, and we have the ability to resist what pandas is going to try and do anytime, as a consequence of something else you're doing, there ends up with some cell of that data frame that doesn't have a value and it needs to put something there. Well, instead of putting a floating point nan and turning everything into floating point, it'll actually represent this as just a thing in the mask, and you'll see the angle bracket NA in the textual representation. In general, be careful whenever you're working, especially with these very small constrained D types or with very large values, because the behavior of pandas to just throw everything into float 64 can lead to issues with correctness, and they can lead to issues with understandability because, originally if you were just working with integers, x plus y would always be the same as y plus x. So that's not anything meaningful to change x plus y to y plus x. But suddenly, if somewhere behind the scenes, pandas changed everything to float 64, that is no longer an assumption that you can make. Additionally, in general, whenever you're working with floating point math, especially with constrained floating point values, float 32, float 16, be very careful. Because float 64 really only starts running into these problems with really large values, 2 to the 53rd at the maximum magnitude. But float 8, float 16, float 32, they start to run into these issues with correctness and exactness, precision and exactness very quickly. And if you are working with constrained floating point values because you're trying to save memory, be really careful, because all of these issues will suddenly arise and you will start to see them cause correctness issues in your code.